Hello, Delaware County Community College students and the local college community. My name is Iain Rakowski. I am a math professor here at DCCC. I have the privilege of presenting to you today the October 2023 STEAM Speaker Series talk. The title of my talk is Probably a Statistician Accepting Uncertainty. One thing that we're going to lead with is the fact that statisticians and mathematicians in general really like puns. So let me go ahead and give you my talk, which will hopefully explain the pun that I made in the title. In this talk, my focus will be giving you an introduction to biostatistics, since this is an up and coming field. What I hope you will get out of the talk is an overview of the role of a biostatistician, an introductory understanding of what medical research may look like, and some specific results from the RAMP paper that I was able to help write. And on a more personal note, I also hope that you get the knowledge that it's okay to be unsure of something, because my path towards pursuing statistics started out with a little bit of discomfort with the field of statistics and not really enjoying probability, believe it or not. So, the overview here is that we're going to look at an introduction of who you're listening to and who I am. I'm going to explain what I mean by probably a statistician. I'm going to talk a little bit about what statistics can do for us by presenting the results of the RAMP paper, the role of a biostatistician using examples from the RAMP paper, and end with a summary of what I mean by accepting uncertainty. So first and foremost, that is me. That's a picture of when I was hiking at Pictured Rocks National Lakeshore this past summer. Again, my name is Iain Rakowski. I am one of the math faculty here at DCCC. I have a Master of Science in Mathematics through the University of Delaware, and I'm currently working on a second Master of Science degree in Biostatistics through the University of Florida with their online biostatistics program. I have been teaching here at Delaware County Community College since summer of 2016, meaning that I have been here for about 7.5, 8 years at this point. I have also had the opportunity of working with some biostatisticians on research throughout my study at the University of Florida and through some internships over the summer with Thomas Jefferson University. Moving into what I mean by probably a statistician, it can really be summarized in a single sentence, and that's that humans have bad intuition for probability and statistics. I teach a lot of the statistics courses here at DCCC, and I have experienced this myself. We have all probably seen something that was probability or statistics related and sort of scratched our head and wondered what was meant by the answer. It might be something that was a pun that your family member gave you. I know my dad really liked math puzzles and puns, things that you'd find in the newspaper. It might be something that you saw in your college studies, or it might be something that you've seen in your own research that just feels counterintuitive. It is pretty common for something that is proven by a statistician to feel a little weird. And the best example I have of that is the Monty Hall problem. A little bit of background before I present the problem. This is a problem that was originally posed by Steve Selvin in the American Statistician in 1975. It actually became famous as a question from a reader in the Ask Maryland column in the Parade magazine in 1990, however. As a result of that Ask Maryland column in the Parade magazine, approximately 10,000 people wrote in talking about this problem. 1,000 of those people had PhDs, and they didn't they didn't agree. Looking at this, a lot of them actually said that the answer to this problem was wrong when it was in fact correct. A famous mathematician, Paul Erdos, actually didn't believe the result until he was shown some computer simulations of it. So, with the knowledge that this has plagued mathematicians and statisticians for decades at this point, let me go ahead and present to you the problem. The situation is that you're on a game show and you're given the choice of three doors. I have a picture of three doors on the screen to help us visualize what's going on here. Behind one of the doors is a car, and you want to win this car. Behind the other two doors, there's goats, because everyone would prefer a car over goats. You're going to be given the option of picking one of those doors. You get to have one choice, and you are going to select the door, and you get whatever is behind the door. Now, for example, let's just make this easy and say you pick door number one. The host is going to try to trick you or try to help you. You're not entirely sure. The host knows what's behind all of those doors. He's going to open another door for you. And for example, say that that's door number three. And he's going to say, okay, you picked one. I'm going to let you know that three has a goat. He's then going to tell you, do you want to stay with door number one or switch your choice to door number two? Again, sort of running through the situation, you're given the choice between these three doors. One of them has a car, you're not sure which. You pick door number one, you're pretty certain door number one has the car. But then the host goes, oh, hold on. Door number three has a goat. Do you want to switch your choice or do you want to stay? Now, the question is, should you switch? And a lot of us will probably have a gut instinct of yes or no. It depends on the person. Personally, I am the type of person in my everyday life where I would say, no, I'm going to stick with my first choice. There's really no reason for me to switch. I had a 1/3 chance now. That door should still have a 1/3 chance. But the problem is that the two remaining doors, if my original door had 1/3 of a chance, those two doors had 2/3 of a chance. The host, by telling you door number three had a goat, moved that 2/3 chance to door number two. So it's actually better for you to switch. Again, feels a little bit weird. Originally, your first door that you chose had a 1/3 chance. Before you knew there was a goat, those other two doors had a 2/3 chance. When the host opened that third door and said there's a goat there, that 2/3 chance had to go somewhere. You didn't find out anything new about door number one, so its chance doesn't change. Door number two is the only thing that we did not know, so its chance is the chance that increases. So again, we should switch. You actually have a 2/3 chance of the car being behind door number two. It's not guaranteed that the car will be there, but you have better luck there. This can be proved with simulations, meaning we can try this experiment over and over and over again, count up the number of times the car is behind door number one and door number two, and about 2/3 of the time the car will be behind door number two. Now, this is not the focus of this talk. I could talk about this for much longer. So if you find this sort of intriguing or engaging, I have a link to some extra reading and a nice video on YouTube by Numberphile explaining this, and there's tons of literature out there for it if you're interested. What I want you to take away from this is that, again, humans are kind of bad at probability when they think about trusting their gut, usually. One more thing, sort of pushing our talk towards the scientific and medical research field, is this idea of P. If we go into medical research or scientific research in general, a lot of people will learn the idea that P less than 0.05 is good. It's not necessarily inherently good. We want to have a better understanding of what it actually means. We don't want to be searching for this dichotomous output, meaning we don't want to be looking for a yes or a no answer. We want an understanding of what it's doing. So, the best example that I've ever thought of or seen or heard to explain what P is something that was actually said to me during my internship at Thomas Jefferson University. The idea here is if you toss a fair coin, like a penny or a dime or a nickel, n times, you would expect about 50% of them to land on heads and 50% of them to land on tails. But let's focus on this idea of 50% of them being heads. So if I toss 10 coins, I'm ultimately going to expect 5 of them to be heads and 5 of them to be tails. Now, we all know from our everyday experience that this probability of 50% isn't perfect. It wouldn't be too surprising to get 4 heads or 6 heads, but it would be very surprising to get no heads or 10 of them. So this cutoff or this value of P less than 0.05 is really meant to give us an idea of where do we transition from saying, yeah, 4 or 6 heads is okay, but 10 is absolutely unexpected. So the question I would ask you, and the question that was posed to me is, how many heads would you need to see after tossing a coin 10 times before you started to think it was a fake coin and that it was more likely to land on heads? Again, what I would ask you is, if I were to toss a coin in front of you 10 times, How many times would it need to land on heads before you started thinking the game was rigged and that this was a fake coin? Some people will say 8, some people will say 7, some people will say 9. It depends on how skeptical you are, and it also depends on the stakes, meaning how important this decision is to you. Now, in your day to day life, you might not care how important is it that this coin is fake. But if we're thinking about medical studies where this likelihood or this idea of whether or not this treatment is fake means life or death, we really don't want to make a bad decision. So looking at coins, if you, for example, are going to say that, 6 heads is, enough for you to sort of start calling the person flipping this coin a cheater. If 6 heads is enough for you to say, man, that coin is fake, then there's actually a 37.7% chance that it's a fair coin. A 37.7% chance that you do get 6 heads with a fair coin. So you'd be calling the person a cheater, and about a third of the time they wouldn't be. Now, if you said 7 or more heads, there's only a 17.2% chance of getting 7 or more heads, which again means that about 17% of the time, if you were to say that this coin was fake when you saw 7 heads, it would actually be a fair coin. Chance just happened to give you 7. Now, if you said 8, 8 is pretty good. 8 is right near that 0.05 idea. 0.05 as a decimal is the equivalent of 5%. So getting 8 or more heads is going to be a 5.5% chance. So if you get 8, 9, or 10 heads, it's a 5.5% chance of getting that. So it's very, very unlikely. But a 5.5% chance does mean that 1 out of 20 times that coin was actually fair, even if you saw 8 heads. Now, we can absolutely be more certain if you see 9 or more heads. If you see 9 or 10 heads, there's only a 1% chance of that happening if the coin was fair. Even more so, if you get exactly 10 heads, if all of those coin tosses end up landing on heads, there's only a 0.1% chance of that happening. So what we see here is a visual example of this idea of p less than 0.05. And what you would find, depending on your field of study, is that different studies and different sciences and different types of research have different cutoffs for this magical value of p. 0.05 means there's a 5% chance that what you saw would have happened with a fair coin. But in some studies, if we're thinking about something maybe like sociology, where we're not going to risk giving someone a medicine that could kill them, you might see a different cutoff, like 10% or 15%. Now, an interesting thing to note, since I do teach statistics, is that we can calculate all of these probabilities using the binomial probability formula. So if you have taken my Math 121 course and we have made it partway through chapter 11, then you'd actually be able to do this yourself and calculate these values I found here. So then, now that I've left you with this idea that probability takes a lot to understand and humans have a bad intuition for it, what I want to transition into saying is that it is worthwhile to spend our time trying to understand this. It's worthwhile to try to sift through everything and make sense of what P means and make sense of the Monty Hall problem and move past that and work through the study of statistics. Both of the examples I just gave you had to do with probability, but probability is this foundation for the study of statistics. So the next part of my talk is to talk a little bit about what statistics can do for us, specifically looking at a paper that I was able to help write. This paper is titled Remote Activity Monitoring: An Electronic Patient-Reported Outcomes Collection During Radiotherapy for Head and Neck Cancer, a Pilot Study. I've highlighted 2 names there. The 4th author is myself, and the 5th author was my supervisor at Thomas Jefferson University. The link to the paper is at the bottom, or sorry, I should say the citation for the paper is at the bottom, and the purpose here was to look at wearable devices like a smartwatch or a Fitbit and see if patients who are going through radiotherapy for head and neck cancer will wear a Fitbit or a smartwatch, And if they wear it, are we able to collect meaningful information about their step data and how they are moving throughout the day to sort of determine or predict whether they're going to have negative outcomes? We did this by looking to see if they wore the device, looking to see what the steps were that they had during the device, and collecting these ePros, or electronic patient reported outcomes, which are essentially survey data. So, what I want to give you here is a little bit of an overview of some of the statistical knowledge that goes into a study like this and what sort of results we can get out of it. What can we tell about the world if we're able to understand the statistics behind it? So, first and foremost, there are tons of different types of studies in the world. This study specifically was a feasibility study, meaning it was looking at a small sample, a small group of people, and looking to see if this was worth scaling up to a larger study. This is a prerequisite to an observation or an observational or an experimental study that you might study in a statistics course. Other types of studies also include this idea of observational and designed experiments. Thinking about studies, we don't just have this type, we have sort of the timing of the study. We have three different types of timing. There's retrospective, going back in time, cross-sectional, looking at a small slice of current time, and prospective, meaning going forward in time. This study was a prospective study, meaning that we recruited subjects and we were following them forward in time to collect data. Retrospective studies are nice because you don't have to follow people over time, they go backwards in time, but they have the downside of relying on people's memory or relying on having this complete data looking back in time. So, prospective takes more time, but is a little bit more reliable. We defined four specific endpoints or goals for this study. Endpoints are specific variables that we want to make sure that we measure. The first one was feasibility. Did the patients wear the device? There actually was a lot of issues with how we define feasibility, and I'll get into that next. Steps was the change in average daily steps as measured by the device. That's a nice, clear numerical variable that we measured there. ePros are electronic patient reported outcomes. These were surveys that were sort of collected and put into a numerical representation by some medical students. And adverse events. This was looking at hospital records to decide if the patients were hospitalized, if they experienced a feeding tube placement, or an emergency department visit. So, what we were able to get out of this is a few different things. In general, statistics have sort of two branches of study. We have descriptive statistics, where you're looking at some data and you're trying to describe that data. And we have inferential statistics, meaning you're looking at the data and trying to predict something about the future or talk about a larger group or a larger population. So, the very first thing that you'll often see in medical studies is a table one, which is a description of the patients that were in the study. What you see here is the top half of our table one from the RAMP study. We looked at the age of the participants, we looked at the sex, and we looked at where the cancer was located. And we split this up by whether or not we were able to collect step data or not. So the first column is everyone in the study. The second column is that we were able to collect the step data for those people. And the last column was people that we could not collect step data from. And what we looked at was to see if there was any difference between their age, their sex, or their disease site. There was a slight difference in where the disease was located, but not a huge difference between age and sex. Then we looked at the clinical stage as designated by the medical doctors that were in the study, the Rakowski performance status, which was also described by the medical doctors in the study, radiotherapy intent, whether they intended to go through radiotherapy, and whether they were going through chemotherapy at the same time. So again, looking at this, we looked at all of the patients, and then we looked at whether they were able to collect the step data or whether they weren't. We didn't see a huge difference in many of these variables, except whether or not they decided or intended to have radiotherapy before the surgery or after surgery. Again, these two tables here are really just focusing on looking at the type of people that were in the study and sort of summarizing it for other researchers. For example, if someone at another university wanted to do something similar, they might be interested in whether they're working with a similar group of patients. Another thing that we wanted to look at was that we discovered a lot of the patients had dates that didn't line up like they should, is probably the best way to say it. We had patients that had these survey data, sort of completed surveys at time intervals that weren't expected. We had patients that wore their device before their chemotherapy or their radiotherapy started. We had people who stopped wearing the device early or started wearing it late. And this was my attempt, what you see on the screen here, to convey to the researchers sort of a summary of everything they might be interested in. One of the very first things you'll probably notice with this, which is called a swimmer plot, is that it's very busy, it's very hard to read, and there's a lot on it. I was actually really excited about creating this because my goal was to give the researcher everything at once. Trying to help you understand this a little bit, moving from left to right is a timeline for each person. Each horizontal line is a separate individual that was in the study. And what I did was I color coded those lines with whether or not they were in compliance, meaning whether or not we decided that they had met the end point of wearing the device. Anyone with a blue line was not wearing the device. Anyone with a peach line was wearing the device. I have filled in circles if they started wearing the device at the very beginning. So we see most of the patients have filled in circles on the left, meaning they started wearing the device at the beginning. And they have a filled in square on the right if they stopped wearing the device at the end of their treatment. We see that near the top, most of those people have worn their device the entire time, but we see that a majority of the patients did not wear their device for the full treatment. They stopped early for one reason or another. Another thing that we looked at was the events. I put a red box anywhere there was a hospitalization, a yellow circle anywhere there was an emergency visit, and a blue triangle anytime there was a feeding tube. What we were interested in here was whether any of those events coincided with when people stopped wearing their device. And we found that that really didn't end up happening. We had people with events after they stopped wearing the device, we had people with events long before, and there didn't seem to be an association visually from that. What ended up happening was I met with the researchers and presented them with this visual summary of the information, and the researchers were able to take from this the pieces that they found interesting and create the plot that we see on the next page, which actually is the plot that made it into the paper. What you find here is that they chose to streamline things by ordering vertically by subject number. They didn't sort by compliance. And they removed the information that they weren't interested in looking at. They really focused only on whether the step data was collected on a specific day or whether it was missing. Any filled in square is missing, so we can sort of visually see where the data started missing from. And they also removed any observations that happened before radiation treatment. This loses some information, but it does clarify the information that they chose to focus on. Another result that comes from the paper is this visual of how a person's daily steps changed throughout time. On the horizontal axis, we see that we have labeled the number of days after the radiation treatment started. So some of our observations started about a week and a half prior to radiation, and some of them followed up to 50 days after radiation. What we saw was that labeling our events all happened for people that had lower step counts, and we also see a high variability of step counts, meaning there's a lot of spikes up and down. We don't have a lot of people that had high step counts that stayed there. Looking at moving into the other type of statistics, looking at inferential statistics, thinking about what can we say about people in general who are receiving radiotherapy for head and neck cancer. One of the first things we were interested in was how their patient reported outcomes, again, this is the surveys, how their own personal observation of their health changed over time and whether their health changing over time was associated with a change in how much they were walking. Helping us to focus on this table a little bit more, I want to look at just the first column. So in the survey, we asked them to rate on a scale their level of anxiety, their decrease in appetite, their fatigue, their general pain, their level of insomnia, presence of mouth and throat sores, nausea, sadness, shortness of breath, and vomiting. What we looked at first was whether these symptoms changed during radiation therapy. Now, from a medical viewpoint, there is an expectation that some of these will change positively, some of these will change negatively, meaning their anxiety might increase, their decreased appetite might increase, their general pain might increase, their sadness might increase, and so on. Looking at the data, we found that many of these things were confirmed. One piece that was surprising to the researchers was that their anxiety actually seemed to decrease over time throughout radiation therapy. Again, here we see a p-value of 0.039, which means that about 4% of the time, if the anxiety did not change, we would still see a decrease of 0.06 in our sample. We might still pick enough people that had this decrease to see this change, even if there wasn't one. So we're pretty confident that there was a decrease in the anxiety. Now, from that, we were interested in looking, was this change in this symptom associated with an increase in steps? Meaning, if the patient increased their steps by 1,000 steps a day, what would happen to their score for anxiety or appetite or fatigue? We only found 2 points of interest here, and what we found was that the level of anxiety in the patients decreased more if they took more steps. Or, again, this is an association, it could have gone the other direction. Possibly stepping decreased their anxiety, or maybe because they had less anxiety, they were going for walks more often. We also saw an association of a decrease in sadness. So again, either people were walking more because they were less sad, or people were less sad because they were walking more. Everything else, we found p-values that indicated it was possible that we would have seen these decreases even if there was no change. So we were not able to report that there was a high likelihood of association. The next result we looked at was the adverse events. We were looking at specifically hospitalization and feeding tube placement. We did not look at emergency department visits because of the number of people who had those occurrences. So looking first and foremost at the very top 2 rows, we looked at their daily step count, and we looked at something called a hazard ratio. What you can think of is a hazard ratio is sort of your risk of this event happening. So for your daily step count over the past 3 days, if you increase that daily step count by 1,000 steps, you had a 40% decrease in your hazard ratio of hospitalization. So you were 40% less likely to be hospitalized. And for a feeding tube placement, you had a 17% decrease, a hazard ratio of 0.83. Again, a 17% decrease of a feeding tube being placed. So we see that an increase in steps decreases your risk of hospitalization and feeding tube placement. Again, we see p-values that say less than 0.001, which means that we have less than 0.1% chance of this occurring in our sample, even if this actual group of people didn't see this change. Looking at the last few rows, we are focusing on, again, those several different patient-reported outcomes from the surveys. The only one of interest we saw was shortness of breath. We saw that if a person had an increase in shortness of breath, they actually had a hazard ratio of 11.54 for hospitalization, meaning if the person had shortness of breath, they were much more likely, or 11.5 times more likely, to be hospitalized. This isn't too surprising from a medical standpoint, but the rest of the patient-reported outcomes didn't have a significant p-value, meaning that we saw a change, but it is not very likely that change indicates that the overall population didn't have a change of nothing. So, ending up this section of talking about the results, 29 patients with head and neck cancer were enrolled and they had analyzable data, meaning we ended up with only 29 people that had data we could look at. Overall, the step data were recorded on 70% of the days during their treatment. So we ended up seeing an average of 70% days where they had step data. However, there were only 11 patients, or 38%, for whom step data were collected on at least 80% of the days during radiation treatment. So we only had a 38% compliance, which was not the goal we were looking for. Also, mixed effects linear regression models, meaning the statistical model that we used, demonstrated that there were declines in daily step counts, and most of their patient reported outcomes got worse throughout radiation treatment. Probably not very surprising to medical professionals. Cox proportional hazards models revealed a potential association between having a higher daily step count and a reduced risk of feeding tube placement and a reduced risk of hospitalization. In the summary for the paper, the main authors said that we did not achieve our feasibility endpoint. Again, this is talking about the fact that we only saw 38% of our patients actually wearing the device as intended. What we took from this was not that the study was a failure, but that it suggests that we need to have a more rigorous workflow and follow the patients and follow up with them and provide incentives in order to achieve this feasibility of wearing this device. Also, we were limited by a small sample size. Despite that, our findings were consistent with other previous reports, which adds to the literature that indicates that wearable device data can help identify patients who might be at risk for unplanned hospitalization or feeding tube. So, even though we had a small sample size, we were able to look at previous reports and find that our information supported these other studies. And again, if we think of this in the terms of the coin tossing, if you toss a coin and it lands on head 7 times, and someone else tosses that coin and it lands on head 7 times, and then someone else does it and it lands on head 7 times. 7 isn't too surprising, but it becomes surprising if it happens over and over again. So, what I want to do is look at this set of study results, all this information I've just given you, and use it to explain what the role of a biostatistician looks like, thinking of this as a day in the life of a biostatistician. When I first started at University of Florida, I attended a talk that gave me a piece of information that really stuck with me. About a third of the role of a biostatistician is the coding and data. You should be able to code, specifically the program SAS was used for all of the analyses in this study. The data were pretty messy to work with, so you want to be able to manipulate data, look at them, summarize them, figure out what's missing, determine if there's any errors. So, about a third of the role is this sort of computer savvy realm of knowledge. A third of the role is also collaboration. A large part of what I did in this study was communicating with my supervising statistician, communicating with the researchers, presenting what I was working on, letting them know if I spotted any issues, and listening to what they had to say back to me and incorporating it in what I was doing. So, being able to work with people and understand people and think about what they're saying is very important. And the last piece, about a third of it, is a strong statistical knowledge. There are so many different fields of statistics to go into, and having a good foundation so that you can add different tools to your toolkit as you're going through these different studies is going to be important. So, talking a little bit more about those three things just in brief, I have an example here that you do not have to read, but an example of what some of the code that I wrote for this analysis looks like. In the larger window in the back, I was looking at the different steps and I was looking at cleaning up the dates that were given to me, different cutoff points for determining if a person was determined as compliant, figuring out if their data, if their step data were within the window, because there were some people that had steps that were long before treatment started or long after, and sort of This is something that I ended up coming back to a lot and sort of editing and changing things based on discussions from the researchers. So writing code that I could read and go back and edit was important. In the smaller window, I have code here from SAS about how to write a mixed effects model, which was the model that was used to see if there was a change in their survey scores or a change in their steps and things like that. Again, all results from this paper were done using SAS 9.4, but as you see in the title of the slide, some other good programs to know would be something like R. SAS is nice because it's used in a lot of industry. It is an expensive program to use on your own. R is nice because it is used in a lot of academics and at a lot of schools, and R is free to use. Talking a little bit more about that first third of the role of a biostatistician is data frustrations. What I have here are just a very, very small snippet of some of the steps that we saw, removing any other information about this, but just looking at steps. On the far left column, we see steps. The second column, we see the number of weeks from when they started radiation treatment. And then the next three columns that have zeros and ones were columns that I created to let me know whether that person was considered compliant, whether that date was on or before their simulation treatment, and whether that date was on or between their actual treatment. Those sort of fourth and fifth columns are both there. We ultimately ended up only using the fifth column because the researchers weren't sure which one they wanted to use, so I created both as we were working through it. The very last column is a moving average of the steps. This was to help smooth out if there were large, sort of quick jumps and gaps to make the data easier to work with. So looking at this, the first example I have here is a person that was actually relatively straightforward and easy to work with. We see that the steps exist for every single row on the left, and we see that the weeks kind of go in increasing values. We go to 3, 3.14, 3.28, and so on. Again, the weeks kind of increase from 3 up to a little past 6. They have some ones and zeros, and they have some values for the average moving steps. Again, this would be some data that is pretty nice and easy to work with. Here I give you one example, and if you are someone who is savvy with data, I might ask you to, sort of pause this video since it is recorded and see if you can figure out what you think might be an issue. But for the rest of us, I'll point out that second column is all negative. That should be the number of weeks from when they started radiation treatment, and they're all negative, meaning these were values I had to make sure weren't included in the analysis because all of this step data was before treatment even started. This person got their device a little bit early and started wearing it before treatment began. Another thing to be careful of is here we see some entries that have dots in them. Dots are the way that SAS tells you that there's missing data. What this means is that you don't have that information. This person has 4 different rows that don't have steps, meaning the person did not wear their device or something went wrong and the steps were not recorded there. That would mean that that person was not compliant, and the problem with missing data is that this person had a decent amount of steps around that first date that's missing. The row before they had 1,800 steps, the row after they had 1,700 steps. So did they not walk at all that day, or did they forget to put their device on? Those are 2 very different types of missing data, and that was something that we struggled with when doing the analysis in the study. So moving on to the second third of a biostatistician's role is this idea of collaboration. For me in this study, it was the statisticians and the medical researchers. As statisticians, I worked under the supervision of a biostatistician at Thomas Jefferson University. I was responsible for the data analysis, writing drafts of the results, as well as interpreting questions into statistical questions if the researchers asked us something. Meaning, if we were talking about the data and they had a question in terms of medical terms or in terms of something they were interested in, it was my responsibility to do what I could to understand what they were asking and bridge that gap into how can I frame this as a statistical question. I also created drafts of figures and tables, as you saw previous in the presentation, and the researchers were able to adjust those figures and tables to suit the paper that they were publishing. The researchers were, again, the medical researchers and the main authors, including the main authors, as well as medical students. The researchers did all of the data collection, all of the interaction with the patients. They formed the questions that were posed and addressed in the paper. They provided medical context for the results that we found. They would let us know if we got a result and it made sense, or if it didn't make sense and there's something we should look into more. And that is mostly to say that they guided what we call exploratory analysis. If we found something of interest, they were able to tell us whether it made sense or whether we should keep looking into it more. Now, the last third of a role of a statistician is a very wide topic. Specifically for this paper, there were three pieces of statistical knowledge that I can identify. The first were mixed effects models. Mixed effects models are something that I have studied at the University of Florida, and they're really nice for dealing with missing data. If you've ever studied statistics and you've learned about linear regression lines or linear regression models, a mixed effects model can be summarized as saying instead of fitting a single line for the whole data, you can essentially fit a separate line for each person with a different intercept and possibly a different slope. So it's useful if you have missing data. Cox proportional hazards models are models that are used for looking at hazard ratio. It is a model, it is a type of analysis that allows you to determine if there is a higher hazard ratio, sorry, a higher risk for some groups than others. As well as just your basic descriptive statistics, which you would study in our Introduction to Probability and Statistics class here at DCCC. This is what was used for summarizing data. We looked at mean, median, mode. We looked at standard deviation. We looked at histograms. Anything you'd see in an introductory statistics class was absolutely used at the beginning of looking at this data. Now, after we have seen a research example as well as an overview in the life of a biostatistician, let me help you see the purpose of the second half of the title, which is accepting uncertainty. Specifically, I would like to show you how probability and statistics can really aid us in understanding a world that isn't black and white. And I'm going to start this by giving you a personal anecdote. Would it surprise you that I didn't like probability and statistics at the start? As an undergraduate in mathematics, I excelled at memorizing and using formulas, but I really struggled to gain a deeper understanding. I found myself disliking probability and statistics for that very reason. However, after I became a professor, I was uncomfortable with this dislike of a part of mathematics. I decided to confront my dislike of statistics by pursuing a second master's in biostatistics. Makes perfect sense, right? Well, what I found was that through my study and research in statistics, I have a new love of statistics, and it ultimately comes from a deeper understanding. I hope that this talk can encourage you to gain a deeper understanding for yourself. Specifically, what I found that statistics gave me were tools to describe uncertainty, a new way to look at and organize data, language to describe the real world and the uncertainty and gray areas that exist with real people, and an understanding scientifically of the need for replication and p-values, knowing exactly what replication means, needing repeated studies, as well as knowing what p less than 0.05 meant. Thank you so much for listening to this talk. If you have any questions at all or would like to discuss any piece of this talk, again, my name is Iain Rakowski. I am one of the math faculty here at Delaware County Community College, and my email is on the screen. It is crakowski@dccc.edu. Thanks again for watching.